Welcome back. Today's goal of this lecture. Today I will see unique factorization domain elaborately. In my previous video, I had defined unique factorization domain shortly. Today I will discuss unique factorization domain when ED imply U.F.D, when P.I.D imply U.F.D. This I will discuss elaborately. At first, see what is the definition of unique factorization domain. In my previous video I had seen also, and I had given the link in description box of my previous video. Please see at first my previous video, then today's video would be more clear, would be more easy to understand better way. In unique factorization domain, factorization should be unique. So this name is unique factorization domain. If R is any integral domain, this is said to be unique factorization domain. That means any integral domain when imply U.F.D, if every non-zero and non-unit element of R can be written as product of irreducible element in R. Okay? And the factorization of element in R is unique up to associate. This factorization is unique up to associate. Consider A belongs to R and A equal to A1, A2, AR and B equal to B1, B2, BS. Notice here all AI is irreducible element in R and all BI is irreducible element in R. Notice here R equal to S, and here these are actually same because here AI is associate with BI. AI is associate with BI. That means here AI equal to U times Bj, where U is a unit in R. This factorization should be unique up to associate. So this name is unique factorization domain. As for example, consider in Z the element 30. In school I had seen in integer every element can be written as product of prime element, and always prime element are irreducible element in Z. So 30 we can write it as 2 times 3 times 5. Also we can write this as minus 2 times minus 3 times 5. Here notice if this is n and if this is m, n equal to m. Number of element here and number of element here are same. Also 2 is associate with minus 2, 3 is associate with minus 3, 2 is associate with minus 2 and 3 is associate with minus 3. 5 is associate with 5 also, because 2 equal to minus 1 times minus 2. Here minus 1 we all of us know is the unit element in integer. Similarly 3 equal to minus 1 times minus 3. Here this is the unit element. So 30 is the example of U.F.D. Okay, I hope my all viewers have understood clearly what is the definition, why this ring is named as unique factorization domain. Here the factorization should be unique up to association, so this name is unique factorization domain. This diagram is very important diagram. If filled, then that imply Euclidean domain. Euclidean domain imply P.I.D. P.I.D imply U.F.D. U.F.D imply integral domain. Integral domain implies commutative ring with unity. Commutative ring with unity imply ring with unity, and that imply ring. But converse not true. There exist many rings when integral domain, which are integral domain but not filled. There exist many rings which are P.I.D but not filled. Not filled, also not integral domain. I will see this proof few minutes later. At first see this property, this is very, if filled, then this is Euclidean domain, P.I.D, U.F.D, I.D, integral domain, CRU, ring with unity and ring. Okay? But converse not true. Consider the example Z-I. Is Z-I is U.F.D? Now notice in Z-I the element 5 is U.F.D because 5 we can write this as 2 plus I times 2 minus I. Also we can write this as 1 plus 2I times 1 minus 2I. These two are same factorization because here the numbers same. Also 2 minus I is associated with 1 plus 2I and 2 plus I associated with 1 minus 2I because minus I times 2 plus I, this is equal to 1 minus 2I, and I times 2 minus I, this is equal to 1 plus 2I. I hope my all viewers have understood. So in Z-I 5 is a Z is a U.F.D because Z is a Euclidean domain, and Euclidean domain always imply P.I.D, P.I.D imply U.F.D. So Z is a, since Z is Euclidean domain, so Z is U.F.D. Similarly, Z-I is a U.F.D. Z-I also Euclidean domain, so this is imply U.F.D. Similarly, if F is a field, then the polynomial ring Fx is also U.F.D because if F is a field, then Fx is always, polynomial is always Euclidean domain. Euclidean domain imply P.I.D, P.I.D imply U.F.D. So if F is a field, then Fx polynomial ring always be U.F.D. Next, is Qxy is P.I.D? Sorry, is Qxy is U.F.D? Notice Qxy is not P.I.D because here the ideal is generated by xy. Here the ideal generated by two elements. So this is not P.I.D, so this is not U.F.D also. We will see one integral domain which is not U.F.D. Integral domain but not U.F.D. That means converse is not true. Z square root of minus 5. This is integral domain and it gives, just recall in previous video, it gives us irreducible element, but it is not prime element. Just recall my previous video. If you don't see my previous video, at first I will highly recommend it you. Please see the previous video. I have given the link in my description box. we can write z square root of 5, the element 6 equal to 1 plus square root of 5 square root of minus 5 times 1 minus square root of minus 5 equal to 2 times 3. Notice here these are irreducible factorization, but these rings are this 2 but is not unique. Why? This factorization is not unique up to association, because 2 is not associated with 1 plus square root of minus 5. Also 3 is not associated with 1 minus square root of minus 5. So the element 6 in z square root of 5 is integral domain but not U.F.D. Also, since U.F.D not U.F.D, that means P.I.D imply U.F.D always. Since this is not U.F.D, that means the converse, this is not also P.I.D, this is not Euclidean domain, this is not field. Okay, this is nice result. Actually z square root of minus d is U.F.D only when, is not U.F.D, sorry, when d is strictly greater than 1, and U.F.D when only d equal to 1. That means this is not P.I.D, not a Euclidean domain, not field. Okay. R be integral domain, then R is U.F.D, then if R is U.F.D, then we all of us know every irreducible element always imply prime element, or if every irreducible element is prime, then R is U.F.D. And this is true also, every irreducible element is prime, this is true also P.I.D. So R is P.I.D imply always R is U.F.D, but converse not true. R is U.F.D does not always imply R is P.I.D. As for example ZX, ZX is U.F.D, but ZX is not P.I.D, because ZX generated by ideal generated by 2 and x, ZX is not generated by single element, so ZX is not P.I.D. Notice one table, Zi. Zi is not field, but Zi is Euclidean domain, Zi is P.I.D, Zi is U.F.D, Zi is integral domain. Z square root of minus 2, this is not field, not, but this is ED, Euclidean domain, P.I.D, U.F.D and integral domain. Z square root of minus 13, I have seen few minutes ago, this is z square root of minus d is Euclidean domain when d equal to only 1, 2, otherwise this is not true. So this is not Euclidean domain, since this is not Euclidean domain, so this is not P.I.D, not U.F.D, only integral domain. Similarly z square root of minus 19, only integral domain. This table is actually very important. Okay, just a nice result. If R is U.F.D, then that imply Rx is U.F.D. This is because if R is Euclidean domain, then that imply Rx is Euclidean domain. Okay, I hope my all viewers have understood clearly what is unique factorized domain and all properties of unique factorization domain. Okay, I will see one question which had come CSR Net 2015 exam. The question is, R be given Euclidean domain such that, but R is not a field. Euclidean domain but not a field. Notice, field imply always ED. ED imply P.I.D. P.I.D. imply U.F.D. U.F.D. imply integral domain imply ring. Here given R is not a field but R is a integral domain. Then the polynomial Rx is always, notice, if R is ED, that means R is imply always P.I.D. That imply this is U.F.D. That imply this is integral domain. But since R is not field, if R is not field, then Rx is not P.I.D. Because if R is a field, then that imply Rx is P.I.D. Since R is not given a field, so Rx cannot be P.I.D. So the principal ideal domain but not Euclidean ideal domain, this is be wrong. This cannot be P.I.D. Since R is not a field, then the polynomial ring since not be P.I.D, so this is not be Euclidean domain. This is also wrong option. Option 3, unique factorization domain but not a principal ideal domain. Notice this result. If R is a U.F.D, then always Rx is U.F.D. Since R is Euclidean domain, that means R is P.I.D, R is U.F.D. Since R is U.F.D, so Rx also would be U.F.D. So this is unique factorization domain but not P.I.D since R is not field. So option 4 also wrong option. This is not U.F.D. This is also wrong option. I hope my all viewers have understood this question easily. Okay. Today I will stop here. I hope my all viewers have understood clearly so far I have taught you. This topic is very important for all competitive exam. In my next video I will discuss some more question about U.F.D, Euclidean domain, P.I.D, irreducible polynomial. Okay. See you soon. Stay safe, stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.